And welcome Calculus 2 students to section 2 of chapter 9. We're going to be looking at the limits of sequences, and we're extending our limit definition to say that we have some function, and let's consider the function to be some sequence of numbers, and then we can extend our limit definition to include the limit of a sequence. And so we now have a formal evaluation for limits of sequences. And consequently, our limit laws for sequences also follow the same properties that they do for functions. If I'm asked to take the limit of a sub n as n goes to infinity, then this would be just the limit as n goes to infinity of 3 n to the third over n cubed plus 1, same as if I was finding horizontal isotopes. This would be what I would call evenly balanced, and so I would take the ratio of the coefficients. That would be 3 over 1, and this limit would then be 3. This one not quite so transparent. For this one, if I'm going to take the limit as n goes to infinity for this 5 plus n over n to the infinity, you know, I've got, I can rework it just a little bit so that I have, let's write limit as n goes to infinity of, oops, and I wrote infinity there and meant to write it n, sorry. Okay. It allowed me to do this anyway. So as n goes to infinity, this is going to go to 0, so I'm going to have 1 to the infinity. If I have 1 to the infinity and I've got this n here, I think what I'm going to do is I'm going to use my log properties. So whatever this limit is, I am going to take the natural log of both sides basically. And so what I'm going to end up with, and I'll write this down. Alright, I'm going to end up with the limit of my sequence is just going to be e to whatever the limit is that I find, because I'm actually taking the limit of both sides, and I'm going to get some L value, and if I don't, then I'll say that this thing diverges and doesn't have a limit. At this point, I did this just so that I could take this n and bring him down front. It still doesn't help me out a whole lot. Oops, natural log of 1 plus 5 over n. However, I can rewrite this as, let's get rid of this in here and just call it 1 over n, because that's another way to write it, because that still is the n up top. And then what I can do is then bring in old L'Hopital's rule, which means I'm going to take the derivative of the numerator and the denominator and then try to take the limit. Because if I look at this, I'm going to have an indeterminate form of 0 over 0, because I'll have the natural log of 1 and this will be 0, so I do have that and then can use L'Hopital's rule. Now that really got messy, but then I can say, when I simplify this, I'm just going to I'm going to multiply this through, and what I'm going to end up with is just 5 over 1 plus 5 over n when I'm finished flipping these things around and multiplying, which then I can say that the limit of this is 5, but that doesn't tell me what the limit of this guy is because it's up here at the top, and that means this is my limit. Alright, next on to C. I'm going to write that the limit as n goes to infinity of this n to the 1 over n. Looks pretty similar to this because I have n in that exponent, so I'm probably going to invoke this taking the natural log of both sides again, so that I will end up saying that the limit as n goes to infinity of this c sub n is going to be e to whatever my limit is, and I'll come back and fill that in. so that I can then say that the limit as n goes to infinity of the natural log of n to the 1 over n, and I can bring that 1 over n out front. And then I get to here, and this limit would then be 0, and therefore e to the 0 would be my limit, which means that the limit of c sub n is then 1. Alright, let's look at this next example. We have a sequence of numbers, and if I were to look at the limit of this sequence as n approaches infinity, I see that this one is evenly balanced and this one is going to be approaching the value of 1. Note that is what it does. I could say that this sequence is monotonically increasing, or I could also say that it was non-decreasing. This particular sequence diverges. The even terms are positive, the odd terms are negative, and it is not going towards any one value. So this sequence is diverging. Let's look at the following sequences in example 3. The graphs are here for you. You can see that the sequence converges to 0 and it is monotonically decreasing. This B sequence here is oscillating back and forth. I can't say it is monotonically doing anything, or I can't say it's either non-increasing or non-decreasing because it's going back and forth. So it's oscillating back and forth, but it is converging to 0. This one is diverging because it's shooting up to infinity, but it is doing so monotonically increasing. This one oscillating and oscillating towards infinity and negative infinity, so it is diverging. Let's look at this theorem here for just a few minutes, and it says we could have looked at our ratio value. That's what this R represents, is our ratio value, and if our R were let's say R were less than 1, then if that absolute value of R is less than 1, then our limit is going to go to 0. If R is equal to 1, then it's going to go to 1, and it doesn't exist if either R is less than 1 or R is greater than less than -1 or R is greater than 1. And we can look at our previous example to kind of verify this. In our minds, we can see that this R value is less than 1. Notice that it is converging to 0. This sequence, the R, is also less than 1, also converging to 0. Note R is greater than 1 and it is diverging, or the limit doesn't exist, also in this D example as well. If you remember the squeeze theorem from a long ways back, what this said is if we have some sort of function or some sort of sequence of numbers that we really can't manipulate in order to get the limit of, if we find a function that is always above it and a function that is always below it, and those two functions that we randomly chose just happen to be going to the same value, and note that C is always above B and A is always below B, but yet they both are converging to the same limit, then we can say that our function that we can't really manipulate also goes to that limit L. So we're looking at example 4. We've got a sequence of numbers that follow this formula here, this cosine n over n squared plus 1, and we're going to need to think of a sequence that's always above it, and we need to think of a sequence that's always below it, and those two sequences need to go to the same limit. And if we can think of two such sequences that go to the same limit, then we can say by the squeeze theorem we know what the limit of this B sub n is. So we're going to come up with a sequence A and a sequence C. All right, in this case it wasn't too difficult because I just used one that was of the form of b. And notice that a sub n is always below or equal to b sub n because cosine n is bouncing back and forth in between 1 and -1. And since the limit of a sub n as n goes to infinity is equal to 0, then, and the limit as n goes to infinity of c sub n is also equal to 0, then we can say from the squeeze theorem, seeing as b is always in between, then we can say that the limit as n goes to infinity of b sub n also equals 0. Pretty crafty. The next theorem just states that a bounded monotonic sequence is converging to a particular value or particular m. And there's a picture that shows us this. In example 5, we're going to look at a bounded monotonic sequence, and the particular sequence that we're looking at happens to be modeling antibiotic concentration in the blood. So we're prescribed a 100 milligram dose of an antibiotic every 12 hours. We're supposed to take another 100 milligrams, and every 12 hours the drug itself has a half-life of 12 hours, so that means every 12 hours only half of it is left. So we're going to keep infusing our blood with this new dosage of antibiotic, and what will happen is we will get a concentration in our blood that reaches a steady state level. So let's start and look at the dosages and see if we can get a recurrence relation. All right, looking at what these dosages do, the first dose is 100 milligrams. The second time I dose myself with 100 milligrams, then I take whatever was there previously, multiply it by half because half is left, and now I have 150 milligrams in my blood. Take another dose. I have 150 milligrams in my blood. Prior to that, 100 milligrams times by 0.5 because after 12 hours, half of that would be gone. Now I'm at 175, and what is happening is I'm taking a new dose, that's 100, plus my previous concentration in the blood, or not concentration, but whatever milligrams in the blood times the 0.5. So that would be my recurrence relation. So how much drug do I have in my system? I need to figure that out from looking at my graph. So if I were to graph this thing, what would I have? Alright, so here's the graph, and looks like after about 10 doses or so you're going to be steady stating it out at 200 milligrams, and that's how much of the blood would be in, how much of the drug would be in my blood after each of these different dosage numbers. So this would be 200 milligrams. From this I would say that the limit of this sequence would be 200, so now we're going to find that direct. Alright, so let's take the limit of both sides of our recurrence relation, and as n goes to infinity, so this is going to equal some value L. Limit of 100 is 100. I'm just using the sum property for limits, and plus 0.5. The limit as n goes to infinity of d sub n is also L. Solving this for L, you get L equals 200. And that's finding it directly. We're looking at the growth rates of different sequences, and they have ordered for us these different sequences, and we just have to kind of figure out which form ours is in. And if the smaller one is on top, that's how they state this. A sub n appears before B sub n, so the smaller one is on top, it's going to 0, and the smaller one is on the bottom, meaning that it's getting bigger on top faster than on the bottom, then it's going to infinity, and that just makes total sense to us. Note that P, Q, R, and S must be positive real numbers, and B right there must be greater than 1. So let's look at what we've got. I can see that using my log properties, this is just going to be like 10 natural log to the n. So this is just some multiple time natural log of n. So I'm sitting here with my a. In my denominator, it is just some multiple of n, and that multiple of n would just be sitting right. Yep, it is right here. I was like, where is that thing? Right here, where p is 1. So my smaller one is on top, so this guy goes to 0. Alright, this guy here, notice that these two guys can be combined, and I have my exponent in the denominator being positive. So there is my a, and n raised to some power, and it is still positive, so this would be my b, and this thing would also go to 0. Here's a factorial. He's sitting right here, and he's way high up there, so that is my numerator. In my denominator, I actually have this guy right here. In my denominator, this means that it's some constant greater than 1 raised to a power, so this thing would go off to infinity because the factorial is going to get bigger faster in the long run. So what you need to do on these is just do that comparison and see which one is most like yours, or which one is a particular form of yours. In this definition of the limit of a sequence, what we're doing is we're looking at the neighborhood of our sequence, those points in that neighborhood, and saying that everything in that neighborhood is going to a particular value. And I'm going to have that neighborhood have a tolerance of this epsilon. And if I can show that they all have this tolerance, all of the points in that neighborhood, I can state that the limit of that sequence is indeed that L. And if I don't have that case, then it is said to diverge. For my first part of this example, I'm to find the value of n that satisfies this neighborhood definition. So let's just go ahead and write down that my a sub n minus this limit, it's got to be less than my epsilon. Let's plug in for what we have, and my a sub n is n over n minus 1 minus, and they say my limit is 1, and they want this given epsilon to be 0.01. Combining this and then doing some algebra, I'm going to get that I have 1 over n minus 1. Since n is always greater than 1, I can remove the absolute value symbols, and I will then, with a little bit of algebra, get that n must be greater than 101. So if n is greater than 101, it would satisfy that epsilon. We're just going to follow the definition of a limit of a sequence and go through to prove that the limit of this particular sequence equals 1. So we'll go ahead and note that given, alright, so we're going to need to find some n such that when I plug it into here, we are, whatever value it is I have for this sequence minus that limit is going to be less than epsilon whenever my n is greater than some value, and I'll need to find that value. We know, as we saw with our values that we plugged in last time, that 1 over this n minus 1 is less than epsilon. So if we solve for n, we will find that n is greater than 1 over epsilon plus 1. So for any tolerance where epsilon is greater than 1, we need to find some n, or we have this capital N, where this exists, in order to be sure that the terms of the sequence are within epsilon of that limit 1. And we can, because we know that we have a value of n for this, the limit exists and then equals 1. So I'll just write that up formally. And there we have it written up formally. If you have any questions about this particular section, please shoot me an email or see me at the Collaborate.